When light passes from one medium to another, it will be refracted depending on the refractive index of both medium. The only time there will be no refraction is if the light enters/leaves an object along the normal empty line. However, as the angle of incidence decreases, more light is instead reflected back inside the medium, instead of being refracted into the typically less dense second medium. The angle of refraction will also decrease away from the normal, until the angle of incidence reaches the critical angle. This is the point where the angle of refraction is exactly 90 degrees and thus seems to travel along the edge of both medium. Beyond this point, all light is reflected inside the original medium instead of being partially reflected. This is total internal reflection. The diagram shows how as light is shown into a different medium at greater angles to the normal, less light is refracted out of the original medium and is instead reflected back at an angle equal to the angle of incidence. This is the angle of reflection. Eventually, as the angle of incidence reaches the critical angle, all light is reflected. As shown by this diagram, light enters the block parallel to the normal, and meets the opposite side of the medium at a 45-degree angle. In this case, the angle is greater than the critical angle and thus the light is totally internally reflected. The angle of reflection is identical to the angle of incidence, in this case 45 degrees, and so it leaves the triangular block with no refraction as seen again in the diagram. Total internal reflection is applied in modern technology through devices such as endoscopes for medical purposes, or in fiber optics that in turn lead to inventive lighting sources and ultra-fast fiber optic broadband using pulses of light. 2 I hope you all enjoyed this presentation of total internal reflection by Jacob Kent. I have been the Windows 10 text-to-speech desktop assistant to transmit data.
And I hope this was somewhat informative. Thanks.